Hello there, welcome to Statistics and Theory. This is Dr. Vahid Aryadust here, and in this installment I'm going to show you how to do IRT analysis or item response theory analysis using the jMetrik software. jMetrik is free and open source psychometric software, and it runs on Windows, on Mac and Linux, so it's pretty useful. If you have not installed the software on your machine, please go to this website and download it from one of these links. The link that I have used, as I mentioned in the previous video, is this one, Windows installer with Java runtime environment, because my machine didn't have the JRE installed on it. In addition, there's a book that the developer of the software has written, Patrick Mayer. I strongly recommend this book because it provides a lot of useful information about how to do the analysis. So if you have already downloaded this software, you will see an icon like this. You double click on it and you open it in this way. As I mentioned in the previous video, in order to use the software package, we have to create a new database. The database that I'm going to create is for this data set. The data set has 10 items, 5 of which are grammar items and 5 of which are vocabulary items. And there's also a gender variable. So let's get started with jMetrik. jMetrik has got this option, manage. Let's go to new database and create a new database. I'm going to call it test 5 because I've created other databases before, and create. So our database has been created now, but there is no data set associated with this, so we have to create that association between this and the data set we have created. So we need to open the database. For the last one which I created is this. I'm going to create and open it, and then I start importing data to, in other words, to associate the data set with it. So the table name which I would like to put, I mean it's arbitrary, but I can use lexical, grammatical ability or anything else. And then I click browse, I go to the desktop. This is the desktop, and I find the lexicogrammatical data set. This is a CSV file, by the way, and click OK. Then import. Okay, our data has been imported, and you can see it from in this corner. If you click on this data set, you can see all the items and also the gender variable available. Next, we should go to transform and click on advanced item scoring. In this tab, we want to specify the scoring rubrics that we have used in order to score these items that you see right in the background. My items are dichotomous, meaning that 0 is a 0 score and 1 is a score 1. So it's basically the same thing. If you have got ABC, you would put down A, B, C, D, and you would provide scores for each of them. But currently we don't have that. Now we need to associate these items with this key. So I'm going to move all items to the right panel, but I'm going to keep gender in the left panel, and then make sure to click submit. I also check options, which is 0 and 1, and scores 0 and 1. So this is a kind of validation check as to whether the scores and the options are the same as those that I have inputted, which is the case here. So everything seems to be fine, and I'm going to click OK and move to the next step. Next, I go to the variable button here and click Fresh Data View, so I'll be able to see if the data type has been specified or not. I can confirm that the data type has been specified accurately, as well as the scoring method, because we've got 0 and 1 under scoring, so this is correct. Now I can start my IRT analysis. Under Analyze, we should go to item response or IRT item calibration, and this menu pops up. We need to select items in our analysis. Click select items, and we have got 10 items here, so you can choose all of them. This is the most like the basic sort of analysis. Since we're doing a basic analysis, it's a good idea to start from rush model or one parameter logistic analysis. Of course, as you know, there is an argument around the idea of whether rush model is analogous to or the same as one parameter logistic model or not. So I'm not going to go through that. For the time being, let's assume that they are either the same or very similar. Then we can go to the next window again. Here we have a few choices to make. So in this tab, let's go to person scoring and put in a name, for example, 1PL, because I would like to save the person scoring or the ability of the persons estimated by 1PL model and then compare it against the ability estimations of the same people estimated by other types of IRT analysis, because I want to see if there is any differences between them. There are different kind of score types or parameter estimation types here. One of them is EAP, which stands for expected a posteriori estimator. The other one is MAP. MAP stands for maximum a posteriori estimator. And finally, the more famous MLE, or maximum likelihood estimator. I'll choose the default, which is EAP, but if you're interested to learn more about these methods, I suggest that you read this paper, which is published in Applied Measurements in Education. I'll leave the link for you in the comments box below this video so you can take a look. And for options, you can leave it as is. Now our analysis is ready to run. I'm going to click OK to get it done. Okay, good. So the first analysis is done. As you see, we have got a parameter. A here is item discrimination parameter, which has been fixed to 1. That's why we do not have any variances, because it's a rush model anyway. The B parameter here is a difficulty parameter, or the location parameter, and it ranges theoretically from -infinity to +infinity. As you see, the standard errors of measurement for each of the parameters have been estimated, and they are presented in brackets in front of them. For example, for the first one, item number 1, the difficulty parameter is -2.46 with a standard error of measurement of 0.10, which indicates that the actual parameter in a large population would fall between -2.46 plus and minus 0.1, which is not a very big fluctuation. So it probably indicates some sort of stability in the parameter estimation. Item 3 here has a very high difficulty estimate as estimated by the rush model, and the reason is that it was not answered correctly by any of the test takers. So it's a very difficult item. If you scroll further down, you'll find that there are fit statistics for each of the items. For example, for item number 1, the chi-squared value is 10.0117 with a p-value of 0.1879. This indicates that there is no significant deviation in the data pattern in this item from the expectations of the rush model. Therefore, this is good. This item is significantly deviating from rush model's expectations. I suggest that you go through the rest of the items and see which one of them is deviating from the expectations of the rush model. That would indicate that the item does not fit the model, or as IRT scholars would put it, that specific model does not fit that specific item. So you can keep these in mind, and perhaps, for example, item 4, V4 and V5, to see if it would be a better idea to fit another model into V4, V5, and V1. It's possible actually under jMetrik to fit different models. into different items. In some items 2, 4, 5, and that's G4 and G5, and V4 and V5 do not fit the rush model. So you can take that into account and then now move to the analysis, IRT calibration, and run a second analysis for a 2PL. By the way, before doing that, what I would like to check again is to see if I can retrieve this 1PL estimation of the difficulty of the ability level of my test takers. I toggle back to variables button here. Sorry, the data button. I still do not see that variable because we need to refresh it. After you refresh the data view, you can see that the variable that you expected to be generated has been generated. There is the parameter estimation for the first person, that's his or her ability level, as well as the standard error of measurement for that person. Next, I'll go back to Analyze. I'll go to IRT again, Item Calibration, select items. I'm going to select all of them and run a 2PL analysis. Click OK. I go back to person scoring and change this 1PL to 2PL. And click OK. Good. So this time around, as you see, the A parameter, which is item discrimination, has been estimated. The best item discrimination would be at least 0.3. In some resources, you'll read 0.35 and above that, because it's analogous to the standardized loading coefficient in factor analysis. So the rule of thumb of 0.3 should also apply here. Anything between 0.3 and 0.5 should be acceptable or above, but it should not get extremely large. For example, as our discrimination parameter gets closer to 2, we start to see some problems in the data. For example, this one is getting closer to 2. You can keep it in mind. And this is, we already know the reason, because it's extremely difficult. Now, the difficulty of this item has changed because we have introduced the difficulty of actually all of the items have changed because we have introduced this parameter into the analysis. We still do not have the rest of the parameters because this is a 2PL model. Now, if you look at the fit of the items, actually most of them have improved, but items V4 and V5 have not improved yet. The rest of them do not have a significant deviation from the expectations of the rush model, which is pretty good. So you can take notes of item V4 and V5 in this time round. So far, it seems that the fit of a 2-parameter logistic model, at least at the item level, is better than that of the rush model. Let's go back to IRT analysis again, change this to 3PL, and go back to calibration, change the 2PL to 3PL. Now I've got 3 parameters here, as you can see: discrimination, difficulty, and guessing. And click OK, and click OK again. And there we are. The 3rd parameter has been generated for us. This parameter is guessing, actually is represented by the lower asymptote in the analysis. Preferably, we would like to see something between 0 and 0.4, something smaller than 0.4 actually. So this one is slightly deviating from that expectation. We can keep that into consideration. And the fit of these two has not, this item and this item has not improved yet, but the rest of the items are actually much better this time around. So this C parameter, or the guessing, has got a standard error of measurement of 0.19, and you can interpret it in exactly the same way as we interpreted the difficulty parameter and the discrimination parameter. For example, for the first one, we expect that the guessing or the C parameter would fall between 0.50 plus minus 0.19 in a larger population, or in a sample which is representative of a population. So it seems that a 3-parameter logistic model is returning a slightly better fit to the data. Next is a 4-parameter logistic model, and that's actually available here. It may not be very commonly used, and there is some criticism of this model, especially the fact that we need a very large sample. That makes it a bit limiting for us in our data analysis. But since we have a relatively good sample size here, that's 1,200 people, we can go ahead and check the fit of a 4-parameter logistic model in our data. So I'm going to go back to this person scoring tab and change 3PL to 4PL and click OK. So the analysis is done. Now we've got 4 parameters estimated for each of the items. And the fit of the test items, I'm afraid, has deteriorated because quite a few of them are not fitting the 4-parameter model anymore, because based on the p-values. For example, this item has item G4 has a p-value of 0.0067. Based on my experience, we often opt for either a 2-parameter logistic or a 3PL model. These two are better cases, and most often 2PL, at least with the data that I've looked into, a 2PL outperforms a 3PL. So I'm not going to go with a 4PL model. By the way, the parameter that we have added here is called a slipping or upper asymptote parameter, which does not seem to be very promising because the statistics are pretty large here. You can use a similar sort of range that we use for guessing and apply it to this parameter as well. And as you see, it's far above 0.4, so I'm afraid this model doesn't look very good. One last thing that I would like to show you before I go to graphs is, as I mentioned before, we can combine different sort of IRT models. For example, in this analysis, I'm going to reset the page. For this analysis, I can apply a 3-parameter logistic model to items G1 all the way to V4. So this is 3-parameter logistic, as you see. And then click Next. And then to items V4 and V5, choose a different IRT model. For example, let's fit a 2-parameter logistic model here. So we have 2 solutions here. Click Next. Well, nothing happens after Next because we don't have any items left. Click OK. Go back to person scoring. Let's call this 3PL and click OK. Nice. As you see, the C parameter has been estimated for the first 8 items here, but it has not been estimated for V4 and V5 because we have got a 2-parameter logistic L2 for these 2 items, whereas we've got L3 for the rest of the items. But did we get any better fit here? I'm afraid not, because the 2 items are still not fitting. So you can permutate this and fit different models into your data, and if you like to experiment with different sorts of models for different kinds of items, you can do that to hopefully arrive at a better solution at the end. Okay, I'm going back to variables data. I'm going to click refresh view, so I'll get to see all of those statistics that we generated before. The ability level of people based on a 2PL, the ability level based on 3PL, based on 4PL, and the last one, which is based on a combination of the 2PL and 3PL. Now, what you could do is let me actually show this because I wanted to go to graphs, but I think it would be useful to take a look at this. We can take a look at the correlation between these statistics. So 1PL, 2PL, 3PL, and 4PL, and 2, 3PL are moved to this side, and we're going to do a Pearson correlation analysis and run the analysis. As you see, the correlation is not perfect, which indicates that it matters if you use any sort of IRT analysis. So that can affect the estimated ability of students. And if the ability of those students, the estimated ability of the students are used for decision making, that can influence their life. So the decision as to which IRT model should be chosen has to be made very carefully. Next, I'm going to go back to graph and non-parametric curves for IRT. So we can create non-parametric curves for all of the items. So I would like to choose item 1 and 2 to move it to this side. And if you're interested, you can also choose an independent variable, an independent variable being, for example, 1PL or 2PL, 3PL, etc. In this analysis, I'm going to choose 3PL because it seems like the theta values, or the ability estimates of people according to the 3-parameter logistic model, was more accurate, as we saw from the fit of the items. So let's move this to the independent variable side. If you are interested to differentiate between the two genders, since you have got a gender variable, you can also move it to group by gender. Let's first do it without gender and then come back and include gender in the analysis. So let's click run. And there we are. On the horizontal line is the theta, or the estimated ability measures of test takers according to the 3-parameter logistic model. The higher the ability, the higher the chances to answer that question correctly. This is for question 1. In the same way, we have a similar scenario for question 2. The graphs are not exactly the same, but they more or less are giving us similar understandings of similar visualizations of the test data. For example, if you have the ability level of 0 logits, then your probability to answer this item is almost 1. So you don't have to have a very high ability level to be able to answer question 1. Similarly, for question 2, you can say that if you have a 0 logit, your probability, your likelihood to answer the question correctly is around 0.85, around that, between 0.8 and 0.89. And this is the test characteristic curve based on the two items. Now, I would like to go back to graphs, to non-parametric curves, and to do two more things. One is to choose all options, meaning that I want to separate option 0 and option 1. That's correct answer and incorrect answers. So it's going to be color-coded, and that's what I was talking about. So the dotted line stands for 1, or the correct answer, and the solid black line stands for 0, or the incorrect answer. So as your ability increases on the horizontal line, your chances to miss that item decreases significantly. So at this point, where the two graphs meet this point of intersection, you stand the same probability or chance to answer the item correctly or incorrectly. That's 50% of chance. On the other hand, for the second item, the chance, this equal 50% chance is at a higher level. That's around minus 0.5 if you compare that. Therefore, item 2 seems to be more difficult than item 1. Another type of graph that you can generate is by including okay, so gender, focal, and reference groups. This is particularly useful in differential item functioning, but it can also give us an idea about how these two groups might be different. Click Run, and there we got it. For focal groups, we have the solid line, and the reference group has been represented by the dotted line, which is red. There is not a very significant difference, at least visually, between the two groups, and here there is also no significant digression from the two graphs, so we can say that there may not be a very significant sort of differential item functioning. But a better idea would be to check differential item functioning through the Analyze menu and differential item functioning through Mantel-Hansel analysis. That will be a topic for another video. Thank you very much for your attention. I hope you have enjoyed the video. If you liked the video, please give it a like and subscribe to the channel. Have a good day.